Okay, ladies and gentlemen, let's continue with forced convection. We already started with convection, and the work is covered in quite a number of chapters. The first chapter that we did was in the textbook of Cengel and Ghajar, was chapter 6 on the fundamentals of convection. Then we also completed chapter 7, which is external forced convection, and now we are busy with chapter 8, which is internal forced convection, which will be followed by natural convection. Internal forced convection is most probably the one, as mechanical engineers, that you're going to work with most. Okay. This chapter, we already started with looking at the difference between external forced convection and internal forced convection. It is about the fact that with external forced convection, the boundary layer may keep on growing, while with internal forced convection, usually the two boundary layers will meet each other. That's the most important difference. Then we've also looked at the entrance region in terms of laminar flow and turbulent flow. And in laminar flow, we have introduced equations that can be used to calculate how long it will take before the flow is fully developed hydrodynamically and thermally. And the difference between them is the Prandtl number. So if you've got the hydrodynamic entrance length, you can just multiply it by the Prandtl number to get the thermal one. Right, so that is for laminar flow. In turbulent flow, it is very easy. Everything happens in 10 diameters. Okay, within 10 diameters, the flow will be fully developed. Then we've started with chapter 8.4, which is a general thermal analysis with specific emphasis on the constant surface heat flux problem and also with a constant surface temperature problem. So with the previous lecture, we already started with this work where we look at a tube. Okay. The inlet temperature Ti, there's a certain heat flux, that would be the outlet temperature. In terms of what we've learned so far in this chapter and the previous chapter is that the heat transfer coefficient would have a certain length before it is fully developed, and also the boundary layer thickness or the CF value, whichever you want to use. And these lengths are not the same, except if the Prandtl number is 1, then they are the same. Okay. But in general, we have a region of developing flow and a region of fully developed flow. Now this sketch is just a schematic, of course. If the flow is turbulent, as we've said, then, and this is a very, very long tube, then all this will happen in a very small distance, and in general, it would be a good assumption to say the flow is always fully developed. Okay, but it depends then on if the flow is laminar or not, and or how long the tube length is in comparison with the diameter. Right, then we started looking at how can we solve sort of what happens on the inside of the heat exchanger in terms of the flow through it and the temperatures on the wall. And this was very easy because if we have the heat flux and we have that temperature, we can actually very easily calculate the outlet temperature. And that is how we did it. And it means the outlet temperature is the inlet temperature plus the heat flux multiplied by P, which is the perimeter. Okay, not necessarily a round tube, but it might be, multiplied by the length of the tube, divided by MCP. So the result of that was that we could get that temperature. Then we also wanted the mean temperature everywhere inside the heat exchanger or the tube. And it was very easy to indicate and to show that it is the equation of a straight line. Okay, so it is equal, temperature is equal to a constant multiplied by x plus Ti. So it's a straight line. Right, so now we have everything of the fluid. So the constant heat flux problem is the easy one of the two, especially getting the fluid temperature. Now we want to get the surface temperature. So we've used that equation. The heat flux is equal to the heat transfer coefficient multiplied by the surface temperature, which varies, minus the mean temperature, and we can also see it is not a constant. Okay. So from here we can solve the surface temperature and we can write it like that. And that is where our previous lecture ended. Okay. Now if we look at this equation very critically, then this is a constant. Okay. That is a constant. It's a constant heat flux problem, so that is easy. The heat transfer coefficient. The heat transfer coefficient is now the one where we have to think about a little bit. If we look at this sketch, we can see that, well, if the flow is fully developed, then the heat transfer coefficient is constant. You agree? Okay. So there it is a constant. So we can say if the flow is fully developed, okay, let's use FD for fully developed, okay, then the heat transfer coefficient is a constant. Okay. And if we can get that heat transfer coefficient, it means that is also a constant, that term. Okay. So we can use that to now determine the temperature of the surface. So in terms of this equation, it would obviously mean the surface temperature is equal to the mean temperature plus a constant C, where the constant C is equal to the heat flux divided by the heat transfer coefficient. Okay. Again, I do not want to draw on this sketch, so I want to ask you to draw the sketch as we develop the problem so that you can see how we start putting everything together. So going back to the sketch now, we have already solved the fluid behavior. Very easy. That's the inlet temperature, that is the outlet temperature. Now we want to get the surface temperature. So if this is known, okay, and we have that temperature, it is very easy to get the outlet temperature. So that temperature there of the surface would be there, and that would be the distance C. Okay. Up to the point from where the flow would be fully developed. Okay. So the temperature Ts of the surface, where x is equal to L, would then be equal to the mean temperature of the fluid at L. Okay. Remember, that is equal to the mean temperature of the fluid, which means it is the outlet temperature, plus the constant C. Okay, I should have numbered that equation as 4 and this one as 5. Or I can then say that the temperature of the surface at L would be equal to the outlet temperature of the fluid plus C, which is equal to the heat flux divided by the heat transfer coefficient. Are you all happy with that? Just looking now, where's my equation 3? And apparently it seems as if I've used that equation as 3. Okay, so this is equation 3, the constant is 4, and that would be equation 5. We will be referring back to them a little bit later. Okay. Okay, so I see my line is not so good here, so it should actually be a straight line. And if you, I forgot, I've asked you yesterday if you've got a red pen and a blue pen, so it would even be better to show that in red, to show that is the hot side, okay, the surface temperature, and that would be the fluid temperature on the inside. Right, so we see that we can solve that. Okay. Now how can we solve the rest? Okay. Okay, so for the developing flow, the heat transfer coefficient as a function of x is needed. So if you know how the heat transfer coefficient behaves in the developing region, okay, then it's very easy to just complete the rest of the calculations. So in general, you'll be able to say then that the surface temperature as function of x would be equal to the fluid temperature plus the heat flux, but now not the heat transfer coefficient a constant value, but the heat transfer coefficient as a function of x. Does that make sense? Okay. So if you can get this, only then will you be able to complete your graph, okay, which again, there's your blue line. That would be the inlet temperature, that would be the outlet temperature, that would be the mean temperature of the fluid as a function of x. Surface temperature here would be parallel to that line. This would be a constant difference C, which is equal to the heat flux divided by the heat transfer coefficient. And take note, this is now where the heat transfer coefficient is a constant. Okay. And to complete it, you get something like that. You need this equation. Okay, let's call it equation 6. So for that part, we need equation 6. Okay, for that one, we are going to use equation 5. Okay, so in equation 6, we need to know how the heat transfer coefficient behaves as it is developing. Then we can get the surface temperature. Okay? Are you happy with the theory? Okay, let's just put together a very simple problem to make it even more understandable. So the problem that we're going to consider is the following. That's the inlet temperature Ti. It's a constant heat flux problem. Okay, the length of the tube is 20 meters, so L is 20. The heat flux Qs is equal to 10 watts per square meter. 10 watts per square meter. And then I've chosen the perimeter, which is equal to pi multiplied by the diameter, as equal to 2 meters. Okay, the mass flow rate, 4 kilograms per second. The Cp value of 25 joules per kilogram degrees Celsius, and the inlet temperature to be equal to 5 degrees Celsius. Okay, you all understand the problem? It's a constant heat flux problem, 10 watts per square meter. Inlet temperature is 20 meters. The perimeter is equal to 2 meters, 4 kilograms per second, Cp 25. And now we have to go and calculate the outlet temperature, the heat transfer, and let's calculate the fluid temperature and the surface temperature of the body. Okay. And later on, I still need to give you the heat transfer coefficient, but I will get to the heat transfer coefficient a little bit later. Okay. So, where do we start? Let's start by looking at the total heat transfer, because we have the heat flux, we have the length, and we have the perimeter. So it's very easy to calculate the total heat transfer rate, which is equal to Qs multiplied by A, okay, or Qs, the area, is just P multiplied by L. The perimeter multiplied by the length through which the heat transfer rate will occur. So we can say that the heat transfer rate is equal to 10. Okay. The perimeter is P, is 2, and the length was chosen as 20. So the heat transfer rate would be 400 watts. You all happy with that? Right. Now, if we have the heat transfer rate and we have the inlet temperature, it's elementary to calculate the outlet temperature. So the heat transfer rate is equal to the mass flow rate multiplied by Cp multiplied by the outlet temperature minus the inlet temperature. Okay. The heat transfer rate is equal to 400 watts. Okay. It's equal to the mass flow rate, and the mass flow rate is 4, Cp 25, so you can see I've selected very easy values to work with, 25, and we would like to calculate the outlet temperature. The inlet temperature is equal to 5. Okay. So from that we can calculate that the outlet temperature is equal to 9 degrees Celsius. Let's develop again our sketch of the temperature as a function of x. So there is x equal to 20 meters. The inlet temperature is equal to 5. Okay, so that temperature is known now. And we've just calculated the outlet temperature as 9. So there we have the outlet temperature as 9. Okay? So that is all that we know at the moment. If you know that a constant heat flux, and if you think about it, is a straight line, then you know that you can just connect the 2 points. Let's just go down one level and sort of prove it and show that that is indeed the case. Okay, so how do we do it? We can just say, well, let's look at maybe the first meter. Let's just look at the first meter. Then the heat transfer rate would be equal to the heat flux, but the area would now be equal to P multiplied by X. It's a surface area. The heat flux multiplied by the surface area, 1 meter. What is it that you do not understand?
No, I don't. You just explain it.
Okay. Yeah. So anything that you don't understand? You're fine with everything? Okay. Okay, so the heat transfer rate would be for the first meter. Okay. Just for the first meter, it would be equal to the heat flux, which is still a constant, multiplied by the surface area over 1 meter. Okay. So we can say that is equal to the heat flux which is equal to 10 multiplied by the perimeter, which is 2 multiplied by x. You agree? Or we can say, question somewhere? No, okay. Or we can say that for the first meter, remember that is now the 20-meter long tube, okay? Just for the first meter, we have the inlet temperature, but now we would like to calculate that temperature, and let's call it the mean temperature, obviously, where x is equal to 1. Okay. So that is our tube, okay, just 1 meter of it. That would be equal to the mass flow rate multiplied by Cp multiplied by Tm, the mean temperature, minus the inlet temperature. Okay. So if we equate that to those two equations, the heat transfer rate, obviously for both of them, should be the same. So that should be 20 times x is equal to the mass flow rate, which is 4, multiplied by Cp is 25, multiplied by the mean temperature minus the inlet temperature, which is equal to 5. Is that, you happy with that? Okay. So if we want to be a little bit more technically correct, let's do it like that. Minus 5. Okay. Because we've set 1 meter, but let's suppose the 1 can also be 2, 3, etc. So it is x, okay? So we can then solve this equation to show that the mean temperature as a function of x is equal to 5 times plus 0.2 times x. So it means for every 1 meter, the temperature is going to increase with 0.2 degrees Celsius. Okay. And again, we can see it is a straight line equation. We can test it for x equal to 0, it would be 5, and for x equal to 20, I hope it is equal to 9. Okay. So the result is now we can say that we have the temperatures in between, and we've connected everything. It is a straight line equation. And something which is very important normally is typically to know what is the mean temperature in the center. The center would be at 10 meters. Okay. So if we go and calculate it, then it would be equal to 5 plus 0.2 times 10, and that would give us a temperature of 7 degrees Celsius. Okay. So we can see the average there, that temperature there should be 7 degrees Celsius. Very simple. Okay, so now let's get to the surface temperature. Surface temperature. For the surface temperature, I'm going to give the following information of the heat transfer coefficient as a function of x. Okay. And the information is going to be that the heat transfer coefficient is going to be a constant of 5 when the flow is fully developed. So if it is 5, when it is fully developed, the heat transfer coefficient. And at this stage, okay, let me do it. Let me say that is 10 meters. So for the first 10 meters, it is developing. The last 10 meters, it is fully developed with a heat transfer coefficient of 5. Okay. So the heat transfer rate is equal to the heat flux multiplied by the area. It's equal to the heat transfer coefficient multiplied by the area multiplied by the surface temperature minus the mean temperature. Or we can say that the heat flux is equal to the heat transfer coefficient multiplied by Ts minus Tm. Okay, this is a constant, okay, for everywhere. All over the tube, the heat flux is a constant. Okay. This one is a constant only for the last 10 meters. Okay. That one is not a constant. We can see the mean temperature of the fluid is changing. Okay. So the surface temperature is going to be a function of x. So if we just rewrite the equation, then we can say that the surface temperature as a function of x is going to be equal to the fluid temperature as a function of x plus Qs divided by h. So it's the same equation that we've derived previously. By just following logic and the simple equations that you know, you should be able to solve everything that you want. Okay, so if we look at this equation, then very importantly, this is a constant, okay, and that is a constant, okay, for x larger than 10. For larger than 10 meters, then the heat transfer coefficient is a constant. So everything there is a constant, and it therefore means that the surface temperature is equal to the fluid temperature plus a constant. Okay. So it's therefore very simple that if we look at our graph again of the inlet temperature and the outlet temperature, like that, Ti and Te, that is the mean temperature of the fluid. Now the surface temperature is going to be that temperature there, and that difference is going to be this constant C, which is equal to the heat flux divided by the heat transfer coefficient. Okay, but let's not go into the calculations. Let's do practical calculations, because that is the purpose of this problem. So what we can say now is, let's consider at x equal L, okay, at x equal L, okay, our mean temperature of the fluid is equal to the outlet temperature, and that is equal to 9 degrees Celsius. Okay, so therefore, if we look at the surface temperature at x equal 20 at the outlet, then it would be equal to the fluid temperature at 20 meters, that would be 9 degrees Celsius. So it is 9 plus the heat flux, which is 10, divided by the heat transfer coefficient, which is 5. So, obviously it's very simple, 9 plus 2. Okay. So that should be 11. But the important thing is the 2. Okay. So the 2 would be that temperature difference there. So that temperature difference between the two lines, so I should have used the red one on top. Okay, so that C, that constant C represents a temperature difference of 2 degrees Celsius between the fluid and the surface. Okay, so now we've got that temperature as 5, that one as 9, and that temperature now is equal to 11. Okay. What would the surface temperature be at 10 meters? Okay. So if we just put put it in, we can see that the surface temperature, where x is equal to 10, would be equal to the mean temperature at 10 meters, and that is equal to 7, which is exactly the average of the two. It's equal to 7 plus 2, and that would be equal to 9 degrees Celsius. Okay, so that is 11, that would be 9, and that one there is 7, and that one is 5, and that one is 9. Okay, let me just repeat, in case it was too fast. Inlet temperature is 5, outlet temperature is 9. The temperature of the fluid in between we could solve. It's on the straight line. With this, we've looked at the heat flux divided by the heat transfer coefficient, 10 divided by 5, so it's a 2 degree delta T, means the surface temperature is 2 degrees higher than the fluid temperature. You can work backwards with the same temperature difference, and now we have that temperature there. Okay? You understand? Simple, isn't it? Okay. Now we need to solve this part. Okay, we can only solve it if we have that average, the heat transfer coefficient, as a function of x. So what I did is I'm going to give that information to you also. And in terms of the heat transfer coefficient, so there is 10 meters, there is 20. Heat transfer coefficient is equal to a constant, it is equal to 5. If x is larger than 10, before that, the heat transfer coefficient is going to be written as function of x, and the function is equal to 200x to the minus 1.422. The heat transfer coefficient as a function of x is equal to 200 times x to the minus 1.422. Right, I can't keep up with all the numbers again. I can't remember where we are, but let's suppose that this is equation 7. So just let's quickly look at equation 7. Px now as a function of x is equal to the mean temperature. It's a function of x plus the heat flux, but now divided by the heat transfer coefficient as a function of x. Which means that that equation we should put in there when we calculate the surface temperature. Okay. Now let's just, for the fun of it, let's go and calculate the temperature of the surface at 5 meters, halfway into the fully developed part. Okay. So at x equal 5 meters, okay, the fluid temperature at x equal 5 meters, it's very, very simple. You can just go and do the calculation with a straight line, but if you just look at this, you can see it should be 6 degrees Celsius. You agree? Okay. Okay. And then we can therefore solve the surface temperature at x equal 5, and that would then be equal to the fluid temperature, which is 6, plus the heat transfer plus the heat flux, which is 2, divided then by 200 times x, which is now equal to 5, to the minus 1.422. And if I didn't make a mistake, then the surface temperature should be equal to 6.49 degrees Celsius. Okay, so let me draw the sketch again. Okay, so the inlet temperature is 5. Outlet temperature. The blue line for the fluid, like that. That would be 5, that would be 9, that would be 7. The surface temperature, there would be a delta T of 2 degrees, okay, which means that that temperature there will be 11, that temperature there would be equal to 9. So at 5 meters, we have solved it as 6.5. I see my scale is not very good here, but in any case, 6.49 degrees Celsius. Okay. So if you want to, at home, please go and put in 1 or 2 more values just to do the calculations. I do not say at all that my heat transfer equation, heat transfer coefficient equation is a good one. I've just put in something to give you an idea of what would happen. So that would be the solution for a constant heat flux problem. For specifically the case where about 50% of the tube, that is 20 meters, that is 10, that is 0, so that was all fully developed flow. Okay. Now, let's look at the same problem and suppose it was turbulent flow. Okay. The flow was turbulent. If the flow would be turbulent, we would know that that is the heat transfer coefficient as a function of x, and that is 20 meters. And P was equal to pi multiplied by the diameter, and that was equal to 2. Okay. Okay, so the diameter should be equal to 2 times 2 divided by pi. You agree? Okay. And it would mean that it would take 10 times 2 divided by pi before the flow would be fully developed. So that is equal to 20 divided by pi, by 20 divided by P, and that would be about 5 to 6 meters. Okay, 5 to 6 meters before it is fully developed. Okay, so if you look now at this tube length of 20, there is 10, there is 5, it would mean that the heat transfer coefficient would typically do something like that. Okay. If the flow is turbulent. Okay. So, with that in mind, what approach would you use if you have a constant heat flux problem? What approach will you use if you do that? Okay, so this is equal to 20 divided by pi before it is fully developed. So if we look at this problem, it's one of those that's now a little bit difficult, okay, because it's about a quarter of the length before it is fully developed. So if, on the other hand, maybe the tube was 200 meters, let's suppose it was 200 meters, then, according to scale, then it would look something like that almost. Okay. And then that value would move to that point there. So So it would be quite a good and a very reasonable assumption to say, well, the flow is turbulent. It means the heat transfer coefficient is almost a constant right through. Okay. You agree? So then the result would be that our fluid temperature would do that. Okay, for all, let's call it practical purposes, the inlet temperature and the outlet temperature, and that would be the surface temperature. And again, that difference would be the heat flux divided by the heat transfer coefficient. Okay, so for turbulent flow, for a very long tube, this part is not going to have a very important influence. But let's look at the opposite of the problem. Opposite. So let's look at a case where the heat transfer coefficient does something like that. It is developing most of the time, and it is almost just fully developed here. So there it is equal to a constant. Okay, so what will now happen with your calculations? We know that the fluid temperature is going to do that from inlet to outlet. That is going to the mean temperature. And the surface temperature now is going to do something like that. Okay. So there's almost never a constant value of Q divided by the heat transfer coefficient between the fluid and the surface. Okay. Now, although this is obviously, as you can see, very, very important to know what the heat transfer coefficient does through the heat exchanger, many people in industry would ignore it, and they would only use the fully developed value. Why? Why? Why would they typically only use the fully developed value and not take into consideration how the heat transfer coefficient changes as the flow is developing? The reason is it gives you conservative values. Okay. So the heat transfer coefficient, what you actually now do is you say, well, that is the average. Okay, I design with it. I know it will be more. And if it is more, I know I can get better heat transfer. Okay. And if by time there's erosion or corrosion or stuff on the outside, I can still deliver the heat transfer rate that I should. So my design is a little bit more conservative. So that is why in many cases people will use the fully developed one and actually not take into consideration how the flow is fully developed. Also, if we have maybe a case like typically the one that we had there, where it does something like that, and that is equal to 5, and that is how the heat transfer coefficient changes as a function of length. It is also quite reasonable to say, well, all this detail is too much for me. I don't want to get involved in that. I'm just going to use the average. Okay. So you go and get the average. Okay. The average, taking into consideration the developing part, and you do all your calculations with that, which would obviously simplify your calculations. Okay, that is the constant heat flux problem. With the next lecture, we will tackle the constant surface temperature problem. Thank you very much.